Sigma notation is a way of writing up the sum or the partial sum of a series without having to write it all out in expanded form. And sometimes we can use it with things that wouldn't have a formula, like the arithmetic and geometric series. We're going to start with some basic examples, though. This one is going to be arithmetic. So you have actually a couple of different ways of writing your sigma notation. So if I had a series, this would be what we would call the fifth partial series, and we're adding up the first 5 terms of a sequence. Remember, the sequence is what generates the list. The series is what would sum up the list. And so the first term in the list was a 6. That's 6 times 1. The second number on the list is 12, which is 6 times 2. Then the third number on the list is 18, which is 6 times 3, and so forth. The other way that we could write it, because this is an arithmetic list, if we wanted to write it this way, just for consistency, we're going to have an equivalent equation. It's just going to be a little bit messier. So it really is just a matter of how do you find the pattern. Can you spot the pattern by just term number times 6, term number 2 times 6, term number 3 times 6, and so forth? Or do you want to actually write it this way, where the first term was 6, and the common difference was also 6 times n minus 1. They generate equivalent lists, so it really doesn't matter which way you do it. Now, the way that we would write this in sigma notation is if you used that pattern to generate the list. So 6 times n would generate the numbers in the list. N tells you the variable that you are using to write your expression. So this variable needs to always match this variable. This is what we call the lower index. It tells you the first number to plug into that formula, and this is the upper limit or index that tells you that 5 is going to be the last number that you plug in. So this is telling you to plug in everything from 1 to 5 to generate your list. And then this sigma symbol right here tells you to add that list up. So the way that we read that is the sum of 6n for values of n, so there's that variable that we're using in our expression, from 1 to 5. So that tells you to start plugging in with 1 and plugging all the way up through 5. So here's your different parts of your sigma notation. We've got our variable, okay, or the index. Remember that this always has to match this. This tells you the lower limit, or the lower value for that index. So this is the first number you plug in, and you plug in all the way up to the upper. The summand is one you're very rarely going to hear us ever refer to. We're just going to say, the equation for the pattern, or we're just going to actually read the equation. I would say sum up 6n from 1 to 5. Okay, so there's a couple of things that we'll ask you to do with this. Expanded form means that we want it written out as a series. We don't want the actual sum. If we also ask you to find the sum, then you would total that partial series up. So this is what it would look like. So here's my pattern, and you notice you've got to pay careful attention. Number 1, there's no parentheses around the 3n plus 7, but number 2, there is parentheses around the 3n minus 6. It's kind of like when there's invisible parentheses inside your square root, where would they close kind of question. This symbol, this sigma symbol, is in your calculator, and all of ours have the new operating system, so there will be little boxes. Those are the equivalent of the parentheses. But this 3n was the only thing inside that sigma because of the lack of parentheses around the 3n plus 7. So the way we would do this is what we're really doing is kind of this. And I wouldn't expect people to write this out, but we're really doing this, generating that list, and then we would add 7 to that list. So this is what it would look like. We would start by plugging in 1 because that was our lower limit. then we would plug in 2, then we would plug in 3, then we would plug in 4. And that was our upper limit, so that's the last number that we plug in. This right here is the sigma notation, the expanded form of it, almost. We need to actually multiply those things. And then we would have the plus 7 at the end. So what expanded form would look like is 3 times 1 is 3, plus 6, plus 9, plus 12, and then of course the plus 7 at the end. If you wanted to, you could put parentheses around that part just so that you would know which part was the sigma notation portion and which was the constant added to the end. But this is what we would call our expanded form. And then if you wanted to, if you were asked to, you would also find the sum. So figure out really quick what that sum would be, and you would have the final answer for that sigma notation. Okay. So you should have gotten 37, right? So then on number 2, we're still going to plug in from 1 through 4, but this time the 3n minus 6 is in parentheses. So I'm going to need a little bit more room, so hopefully it's okay. I'm going to come over here and I'm going to erase just this edge over here to give myself some room. Okay, so this time around what I would do is I would plug in the 1, but this is the whole expression. It's the whole pattern equation. Plus, because there's going to be pluses in between all of our terms because of the sigma symbol. Then I would plug in a 2. So there's the second term. I'm going to jump down to the next line because I need the room. Then I would plug in the 3. So there's the third term. And then I would plug in a 4. And there's the final term. And then I would need to actually figure out what each of those 4 terms is. And you also have to pay really careful attention because we're not always going to start with a 1 down here. I might only tell you to go from term 3 to term 7, something like that. And it's only when we go from the first term to a certain number that we can say, we can use this notation as well. This would be the 4th partial sum of that series. If I start at, if I have a sigma symbol that starts at 3 to 7, I can't call that the 7th partial sum. It's not, because I'm missing the first 2 terms in that series. So you've got to be really careful about the notation that you use and how you read it. Okay, but these individual terms, so 3 times 1 of course is 3, minus 6. So negative 3 would be the first term. Then 6 minus 6 would be 0, would be the second term. Then 9 minus 6 would be 3, is the third term. And then 12 minus 6 is 6. And there's the 4th term. So here's your expanded form. And then the actual sum of that, of course, would just be 6. And that would be your final answer. Okay? So now going in reverse order, you have to determine what kind of list generated the terms in your series. Remember, the word series has nothing to do with the individual numbers in the list. It's just telling you to add up those individual numbers in the list. So when you're trying to figure out what kind of pattern it is, you treat it more like it's a sequence. You treat it more like this. Okay, because I just want the equation for the pattern that would have generated the numbers in the list. So what I do is this. I look at my list, I can tell that I'm adding 5 each time. That makes it arithmetic. So I write the pattern for it, the equation for it. And I can simplify it if I want to. So my first term is 10. My common difference is 5. So there's the equation for my pattern. If I want to, I can go ahead and convert it into slope-intercept form. And those would be my 2 options for the equation that's going to get written in sigma notation. Okay, but I'm not done with my sequence formulas yet, and you'll see why in a second. So My sigma symbol takes care of the plus signs. That's what tells me to add all the numbers up. I'm starting with the first number in the list, which was 10, so I'm going to start with n equals 1. And I'm going to go ahead and, just because it requires less work, I'm going to use the point slope form of my pattern, just because that's also the version of the equation we give you on the quiz and the test and that kind of thing. But then the reason that I'm not done with my sequence formula yet is because I don't know what term number that is. And so I don't know what my upper limit on my sigma notation is going to be right over here. So I need to figure that out the same way that we did on our series notes, the same way that we did on our sequence notes. So I take my equation, either one of them. So I'm just going to, once again, I'm going to work with my original version, just because that is the one we use more frequently, just because it's less work. And I'm going to set it equal to 100 and figure out what term number that is, so I know what was the last value for n that got plugged into this equation. So I subtract 10. Then I divide by 5. And then I add 1. So this right here is the 19th term. So it's term 19 in the list. And that tells me that the upper limit over here is 19. 19 is the last number that's going to get plugged into that equation. Okay. So now, once again, I'm going to need more room. I want you guys to take a second while I'm doing a little bit of erasing. And I want you guys to start finding the equation for number 4. And you can always feel free to pause it if I'm moving too fast, if you want to actually try the problem. I just want to keep the notes as short as possible and still explain everything. So once again, remember that when you're writing the equation for the pattern, you're treating it like it's a sequence. Okay? And this is a very finite sequence. We can already tell what our lower and our upper limits are going to be on our sigma notation because there's no ellipsis, that dot, dot, dot. So we know that this is going to be the first term in the list, and we know that this is going to be the 6th term in the list. So the sigma symbol will tell us to put pluses in between those numbers. We're going to start by plugging in 1 to the equation for our pattern, and we're going to end by plugging in 6. And then we just need to figure out what is the equation for the pattern. Okay, so this time we can tell that we're multiplying by 2 between every 2 terms here, which makes it exponential or geometric. And so that pattern's equation would just be term 1 times the common ratio to the power of n minus 1. So my first term was 5 times, and my common ratio is 2 to the power of n minus 1. I don't have to have parentheses because this is all one term, it's being multiplied, but if you want to be on the safe side, you can always put parentheses around it, like that. And also keep in mind that if your common ratio is a negative number, or if it's a fraction, you're going to want to put it in its own set of parentheses as well, just to make sure you're careful with PEMDAS. Okay, so the last 2 examples are ones that are not arithmetic and geometric. That doesn't mean you can't write the equation for it. So, process of elimination, you rule out that number 5 is not arithmetic, it's not geometric, because you can tell you're not adding the same thing or multiplying by the same thing each time. So that means that there's going to be either a relationship between the actual term number and the term values, like on the exploration we did in class, or there's going to be some kind of recursive function, which we don't use with sigma notation, so you're still pretty much home free. for those. So remember to write the term number underneath or above, and you can theoretically spot the pattern. So term 1 was 1, term 2 was 4, term 3 was 9, term 4 was 16, and so forth. So hopefully that means you can spot that all we're doing is taking the term number and squaring it. Now this list starts down here with term 1, but you notice there's an ellipses at the end, and that means that it's going to keep on going forever, so on to infinity. And so I couldn't actually ask you to sum up this entire list because it's not possible. And the same thing's going to go with this one. This one is what we call harmonic. It looks like you've got a convergent geometric, but you don't, because you're not multiplying by a common ratio that's making your numbers get smaller. So once again, you rule out arithmetic and geometric, just process of elimination. And then you figure out, well, there's got to be a relationship between the term number and the term value. So term 1 was 1, which is 1 over 1, by the way. Term 2 was 1 over 2, term 3 was 1 over 3, and term 4 was 1 over 4. And so once again, theoretically, you could figure out that my pattern was just 1 over the term number. The sigma symbol will take care of the plus signs in between them. We started with term number 1, and the ellipses at the end means that we're going to keep on going for all eternity. So those are the two sigma notations for those patterns. So just because something's not arithmetic or geometric, number 1 doesn't mean you can't find a pattern for it, and number 2 doesn't mean you can't write sigma notation for it. Okay, so that's it for tonight's notes. We're going to come back tomorrow. We're going to work some more in class. Remember, you've got a sequence quiz, that kind of stuff. And then we'll take a day off of notes and we'll do some group work the next day. Let me know if you guys have questions when you come to class.